Hi, this is an absorption and stripping problem. So in this scenario, we're absorbing hydrogen sulfide into water, and so this is an absorption problem since we're going from a gas to a liquid. And we want to remove 97% of this. And then they're asking us to basically find the outlet gas and liquid mole fracts, the equilibrium stages, and so on. So it's pretty standard McGill problem. And as we can see, we also assume that the total liquid and gas flow rates are constant, and since these concentrations are so low, we can basically assume the streams are dilute, so we don't have to worry about using mole ratios. We can just use mole fractions and we should be fine. So let's just start by drawing out the process. So we have an equilibrium, we have a tower, and we have water going in, and we have a gas that's going in, like this. So the water is flowing in at 2,000 kilomoles per hour. And the gas is flowing in at 10 kilomoles per hour. The concentration of the hydrogen sulfide is 0.00012, if I'm not mistaken. Oh, so I add an extra 0. And this is the concentration YA. And then we want to remove 97% of this, and so the first step is to find the outlet concentrations, and we can do this with just a simple mole balance. So if the mole fraction is 0.0012 and we have 10 kilomoles per hour, this is equivalent to 0.012 kilomoles per hour of HS, H2S. And so we know 97% of this is going into the water. So 0.012 times 0.97, and then this divided by the total water flow rate. So this is the amount of moles, kilomoles flowing out of the water. So this divided by 2,000 is equal to the concentration of hydrogen sulfide in the water, and this gives you a value of 5.8 times 10 to the minus 6. Being the same thing, so now for the gas flow, so we know that it's 0.012 times 0.03, or 3%. Divide this by 10, and you get 3.6 times 10 to the minus 5. And so those are our outlet concentrations. So this is XA, and this is YA. Okay, so now for part B of the problem. Now, if you look at, so we're asked to do a McGill equilibrium stage calculation. So if you look at the equilibrium data that the book provides, it's actually in the form of Henry's law constants. So the equilibrium equation is actually H, so Y is equal to H over P times X. So now all we have to do is basically plot that and then draw our operating line. Just to remind you, the operating line equation is Y is equal to L over V times X plus Y1 minus L over V X0. Okay, so I've taken the liberty of setting up an Excel sheet with the values that we've known or we previously calculated. So you can see here that we have Henry's law that was taken from the textbook, and we have the column pressure. And we also have the flow rates as well as y1 and x0, which we know from the problem statement and from calculating it in part A. So let's start by drawing our equilibrium line. So we know that our equilibrium line is simply h over p times x. So I've gone ahead and made a few reference x values. So this is simply h divided by p, and this should just be constant reference times x. And then we have the equilibrium data, and let's go ahead and plot this. There. So now we have a nice equilibrium chart. And let's do the same thing for the operating line. So the operating line equation is L over V, so L divided by V times X, plus Y1 plus L over V X0. X0 is 0, so we can just ignore that, and we can just add Y1, and that should be sufficient. And let's just make sure that the cell values don't change. And there we go. So I'm going to add another series. The x values are going to be this once again, and the y values are going to be my operating line. And there you go. So now we have both of our values, and as expected, the operating line is above the equilibrium line, which is what should be the case for an absorption problem. I'm going to add some trend lines here so we can clearly see where the lines are. Okay, so now that we have our chart and it's imported into OneNote, let's just step down the column and find our number of stages. So just as you would typically do in any McGill problem, you start from the inlet concentration, which is 0.0012 right here, and you step all the way down to the concentration, Y1 concentration, which is actually right at the end of the operating line over here. So we're just going to go all the way down. So we're going to start here and go like this. And then number of stages is simply the number of times we touch the equilibrium line. So let's just count them by, let's just count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 stages, and therefore that's the answer to part B. Okay, now so for part C, they're asking us to find L over V min, and which means that we're trying to find a pinch point. So if we go back to the diagram, we know that if we adjust the water flow, right? So let's adjust this to something lower, like 1800. You can see that the operating line and the equilibrium line get closer and closer together. And we're essentially just to find the L over V min, we need to find the pinch point at y equals 0.0012 because that's where our column begins. So to reiterate, we're looking for y equals 0.0012. So let's start by finding the correct value of x where the two lines need to intersect since the equilibrium line doesn't change. So 0, so 0.0012 is equal to, and the equilibrium relation is 423 over 2.5x. And so if we solve for x here, we find that x is equal to 7.092 times 10 to the minus. We need to write out our operating line equation. And so our operating line equation is equal to y equals L over V times x plus y1. And then the rest we just ignore because x0 is equal to 0. So let's start. 0.0012 is equal to L over V times 7.092 times 10 to the minus 6 plus 3.6 times 10 to the minus 5. Right? So now we simply need to solve for L over V. And when we do that, we find that L over V is equal to 164.124. And so the question, so that is L over V min. And the question was not L over V min explicitly, but it was to find the multiplier if L over V is equal to the multiplier times L over V min. So basically, L over V is equal to M times L over V min. So just solving for this, so 200 is equal to M times 164.124. And then, so finally, we find that M is equal to 1.22. So finally, for part D, this is just a qualitative problem. So why is this process not practical? Because if you can see, the water flow rate needed for this is really, really high for a really small gas flow rate. So it's likely not economically or very easy to implement. So in order to solve this, you'd use something with a more favorable equilibrium curve. So you'd use either a different solvent, or you'd use chemical absorption instead of physical absorption. Or worst case scenario, you could even lower the temperature of the water, because then your Henry's law constants are more favorable. But in its current state, the equilibrium values are just not great for absorption of hydrogen sulfide.